Let me the microphone.
Let me use this one.
Oh, okay, this is this.
Okay, welcome people to the pre-seminar. It's a pleasure to have Aaron Kettner, who's a local here, to speak about the group von Neumann algebras. Please.
Thank you. All right. So, yes, first of all, in case anything is not readable, both for the people here as well as online, that's very likely considering both the blackboard and my handwriting. Please tell me immediately. Okay, one more thing. This pre-seminar is supposed to be for discussion, okay, and I want to encourage that. So at this year's Rhymes History, there was a talk where the speaker asked questions to the audience and then rewarded correct answers with chocolate. Okay. Now, this is going to be easier. I will reward you for asking questions. So I have any PhD student or postdoc asking a question, I will throw some chocolate in. This is not vegan, there's also some fruity stuff which is vegan for us. Please ask me questions. All right, let's start. So some motivation. We have a group gamma. Should I close the door? No. If we look at the group gamma, we can form a discrete group. We can form its group algebra. Okay, so this is just like the linear span of group elements with complex coefficients. And for finite groups, this is apparently a very useful thing because it has the same representation theory as the group itself. That's what I heard, at least. But this is not an action or anything. Okay. Okay, so if the group is infinite, like the ones we want to consider, then this is an infinite dimensional algebra, right? And I know about you, to me that kind of screams function analysis, because if things are infinite dimensional, so, I mean, if things are infinite dimensional, interesting stuff can happen. So we could try to put a norm on this, turn it into a Banach algebra somehow. And that's kind of what we're going to do. In fact, we're going to turn it into a Banach algebra, which is a super nice kind of, right? Yeah, and I often heard that this kind of representation theoretic point of view was actually the original, or one of the original motivations of Murray and von Neumann to start looking at operator algebras. I tried looking at the original paper, Rings of Operators, but it's like 100 pages long. I gave up after reading the table of contents. But if you want to, please have a go. I'm sure it's interesting. So let's just do the construct. Again, gamma part of the discrete group. We can consider its left regular representation. Of gamma on the space small l of gamma, which consists of functions from gamma to complex numbers, which are square summable. Is there anybody here who has not seen this before? I don't know about.
So how do you take a sum if G is an infinite group?
Oh yeah, I mean this is like so you demand the series to converge, right? So otherwise we only look at functions that converge. We only look at functions such that the series converges. Right? Otherwise this condition would be kind of void if the group is finite, because then the sum is automatically.
Is the goes for example, that was something for general groups. With confuse how this works.
It is discrete and countable.
So it's a countable group. Okay.
Yeah, exactly. Okay, great. Yeah. You like chocolate? Let me try that again. Yes, so this is the Hilbert space, right, with the inner product that I guess is the standard one. Everybody's seen this before. Then I don't need to write it down. Now we consider we have an orthonormal basis of this Hilbert space. We consider the following vectors: delta S and T, where S and T are in gamma. This should be 1 with S equals T, and 0 otherwise. Right, so basically what happens is you have, let's say you have the integers. 0, 1, 2, minus 1, so on. Is there some color chalk? So let's say, I don't know, delta 1, that would be equal to 1 here and 0 everywhere else. Okay, guess that's clear. So those are like the unit vectors somehow supported on group elements. And this is an orthonormal basis of the Hilbert space. So the collection of all these delta T or delta S or S and gamma is an orthonormal basis of the Hilbert space L2. Now, the vague strategy for turning this into a phenomenon algebra is to represent it as operators on the L2 space, and then we can take some closure, okay, to turn it into an actual operator. So we need to somehow associate, like we need to represent our group on the surface, right? I mean, we need to form the regular representation, which is given by taking lambda S. This should act on delta T by shift. So this is delta S. Okay, so what we do is just, we shift downstairs on the level of the group. In this example, let's say we take lambda minus 2 of delta 1. Then we're minus 1. Just check.
Oh, okay, yeah. Oh, so there's a count on. Yeah, okay.
All right, so this is an orthonormal basis. The delta is form an orthonormal basis of a Hilbert space. So it is enough to specify what this operator should do on this orthonormal basis, right? That determines it uniquely on the Hilbert space. And another thing is that this is just shifting. It doesn't change the coefficients. It doesn't change the values of the function. That just puts them somewhere else. So this operator is unitary. It preserves the inner product. Okay, so for all s like that, we have the lambda of S. This is the unitary operator, and then we have gamma. And well, it's easy to see that lambda of S T equals lambda of S lambda of T. I guess that's kind of clear. If you shift twice, that's the same as shifting with the product of the group elements. So this is a unitary representation of. And this is called left regular representation. Left regular because we multiply. And furthermore, it's injected. So the identity on the Hilbert space this implies S being the identity of the group. Right? Because if it's not the identity, then we are shifting somehow. So it can't be the identity unless S itself is there. Which means that we can regard gamma as a subgroup of the unitary group. Now we take the span, so the span of this linear span. Now this will live in G of H, part of P of the 2 of gamma. And this is isomorphic to the group algebra that we started. Right? We just take linear combinations of those guys, but this is isomorphic to our original group now. So this is isomorphic to as a complex algebra, I guess. This is isomorphic to the group algebra, and it's so this is first of all, this is isomorphic to the second of all, this is a star algebra. Because we look at lambda of S star, then let's just say it's lambda of S plus. That's something you can just check using how the inner product is defined and how this guy is defined. Yeah, because the adjoint is somehow shifting in the reverse direction, which is just shifting at the inverse of the group. Okay. Now this is nice. I mean, we have a star algebra, which is a sub-algebra of the bounded linear operators on suburban space. So now what we can do is just take G, define this as the linear span of lambda of gamma closed in the strong operator topology. Okay, so a little reminder of the strong operator topology of reminder if H is the original. So we have a sequence of the operators in D of H. Is that still really close to? Then AN converges to some A in the strong operator, which is only if it converges pointwise, basically. So for all vectors in the over space, AN applied to that vector converges to AN applied to that in the norm. Okay, so this is like pointwise convergence in norm, strong operator topology. And this is what we want to take the closure. Yeah, it's the G side of bracket. Oh, that is you vegan? Okay. And this is our group. Okay, so this is why is this a phenomenon algebra? Is there anybody who doesn't know who does not know what phenomenon? Okay, great. Then let me quickly talk about that. So I guess all of this is over. Oh no, how? We have more space. This is actually nicer than. It's basically exactly the thing we just constructed. It's a that's one. There are two possible definitions. One of them is H is clear space. Then a phenomenon algebra It's star algebra. P of H that is close to the strong operator. So that's it. So it's kind of immediately clear that this is from Neumann algebra because we defined it this way. We took the closure and the strong operator. There's another equivalent definition, which is it's a C-star algebra with a predual. So like it's a we define it as a C-star algebra. For that, we need to know what a C-star algebra is. So that might not help very much, but such that it's a Banach space. A lower star such that Newell space of a lower star is taken. And now what's a C-star algebra? C-star algebra is an involutive Banach algebra such that the C-star identity. So that would be like the axiomatic way to define this, but this is somehow the concrete way, and this is what we will need. Does that make sense to all of those people who raised their hands? So it's, yeah, you just take some Hilbert space, bounded linear operators, and then look at a subalgebra of that. So it's like it's literally an algebra of operators.
Just a stupid question because I don't remember how. The two is a C-star algebra. You're looking at all the linear functionals on C-star algebra and then starting with the norm from.
Yeah, so this is just as a Banach space, really. So it's just all. Yeah. So I'm just saying, like the algebra structure doesn't matter here. So it's really like what you said, all the continuous linear functionals, where continuous is in the norm topology.
And then the norm is just different.
I mean, the norm is the norm that you have. It's a Banach space, right? So like it comes with the norm.
Yeah, that's true.
So yeah, this is the phenomenon for basically so this is, we would call this the left regular, the left group phenomenon, because you use the left regular representation. You could use the right regular representation, where here you would kind of shift from the opposite side, but that gives you something isomorphic. So I guess it doesn't really matter what you use. Okay, any questions about anything? I don't know. What's a Hilbert space? What's anything?
Is very tangential, but I have a feeling that sometimes you can say this pre-dual is unique. You know anything?
I thought it was always unique. I think for phenomena, because you talk about the video.
Yeah. So okay. But
I might be wrong. I mean, I haven't looked at this in some.
yeah.
Yeah, it's just a function of the normal, right? The normal function.
Yes, but I think it's still I think it was proved in some paper. This is unique.
Yeah.
Anyway,
You throw blocks at non-postdocs.
I'd rather not.
Thank you.
Anything else? Because I guess, I mean, we would enter a slightly different section now, so this would be a good chance to ask. So basically, just to recap, one last time, we took the group algebra and we wanted to make it into something operator. Right? So we represented it concretely as operators on some Hilbert space, and then we took the strong operator topology closure, and that gives us. So that's around 10 minutes, right?
Yes.
Okay, then we will now talk about something else. Something that will appear in Patrick talk in a few minutes. Topologies on some spaces, for example. Okay, so first of all, we consider again a countable discrete group. I won't write it down, it's already here. We consider the space of all subgroups. Okay, so when I write with less or equal sign, I mean that H is a subgroup. Okay. We consider the set of all such subgroups, and now we want to equip it with a topology. So this space becomes a compact matrixing space. The Chaboti topology, I meant to ask you how this is pronounced, but I forgot. So Tatomasi, is that the Chaboti? Chaboti topology, all right. So this is generated by Newton sets of the following form. You have one of you take so this contains all yes. This contains all subgroups of gamma, such that H and U have non-empty intersection for some subset should be a subgroup phase. Sorry, I also makes sense here. Yeah. Use a subset of this, but then what is this intersection? Wait, no,
H is inside U.
No, I remember that there was this, like this is correct, it's just somehow either this or this I messed up, so I think my notes here are a bit, it's probably something incorrect. Okay, well maybe this is actually subset and not an element. No, but that doesn't make sense. Oh. Okay, I mean, Tatomasi, you will have that.
Yeah,
I remember right. We'll define that again. That's a bit upsetting though. It's now the second set, which will have the same issue. So suppose this means all subgroups of gamma such thing. I mean, okay, maybe that might be a I don't know that like a subset. It might just be a subset of gamma things.
It's like the open ball around you.
Makes
It's like, no, that's an open ball around you or something, I guess.
Yeah, right, that makes sense. Okay, so that, yeah, that should be. Yes. Figure that out, so. Here we take a compact subset. Okay, so we have these two types of open sets. This should be empty. One where we demand the intersection to be empty with a compact set. Compact in our case just means finite because it's a discrete group. Here we we demand the intersection to be non-empty. Yes, so this is a bit random now. Okay, this is just to prepare you for Tatomatsu's talk, because this will play a role, and obviously, so yeah, just take it as a fact. You have the space of subgroups. You can put this topology on it with this topology. Right, that's publishable. Now we have a similar topology on the space of all subalgebras of a Neumann algebra. Okay, so that's Neumann algebra. Space of subalgebras. And then we can define the Meller-Schall topology. Okay, so this is a bit different, but similarly obscure. So we first define the limes inferior of the sequence. So we will basically define what it means for sequences to converge. For that, we first define the limes inferior. So I guess this is a sequence. Yeah, this. So this. So we take sequences in our bounded sequences, choosing one element of the sequence each from one of the Neumann algebras that we have, right? So we have like these are the Neumann algebras. We choose the sequence by choosing elements from each of these Neumann algebras, and then we ask this to converge to something. So if the sequence converges in the strong star topology, then this the thing that it converges to should be in this limit. Now, what is this guy? The strong star topology. This is so this is equivalent to xn converging to x in the strong operator topology and the adjoint converging to the adjoint of x in the strong operator topology. Okay, so this makes sense because the adjoint is not continuous in the strong operator. Okay, so just because xn converges to x doesn't mean that the star also converges to the star of x. But so we can if we put that as an additional assumption. That's that. Now we define the Lim-Suk. Similarly, so basically it's exactly the same thing, just that instead of the strong star topology, we take the weak operator topology. What's the weak operator topology? The weak operator topology weak operator topology is basically you evaluate the sequence against all by taking inner products with all elements in your Hilbert space, and that's that approach. In our Hilbert space. Okay, so if you think of operators as infinite dimensional matrices, then this just means that the entries converge separately. This is the weak operator topology. Okay, now we're almost there. So now we define convergence in this was Maréchal topology.
I guess that if you converge with respect to the strong operator topology, then applies convergence with respect to the graph.
Yes, that is correct, because the inner product is continuous. So if this guy converges,
Yes, of course.
then it will be convergent. Okay, so now our sequence of von Neumann algebras converges to a given von Neumann algebra if both the lim that we defined up there and the lim sup are equal to that one. And I mean, there's a lot of stuff under the rug here. I guess you need to show that then this notion of convergence actually defines a topology and so on. So, apparently this works. So that's the definition of the F-cross Maréchal.
You probably have to look at the volume algebra exemplified by lim sup.
Yeah.
The definition, it should be the lim sup. It should be the volume algebra exemplified that.
Okay, sorry. Then it's like the, so you take like the span and the.
Yeah, basically look at the double commutant.
Okay, that's good. I need to explain what that is. Okay, the double commutant is the same as the strong operator project. So, just ignore that. Okay, so now we're basically done. We're prepared for Tetramassy's talk. We have to recap. We have subgroups of our given group. We put that space with the topology. We have the space of algebras of a given von Neumann algebras. We put that with the topology. Now there's one last thing, which is kind of a cliffhanger, which I hope Tetramassi will resolve. So the von Neumann, the group von Neumann algebra construction that I showed you in the beginning is functorial. Okay, so meaning in particular that if I have H being a subgroup of gamma, I get the L of H is a subalgebra of everything. Okay, so in particular there is an obvious map from this space of subgroups of gamma to this space of subalgebras of gamma. We just map H to L of H. And now since we have two topologies on these spaces, it's natural to ask is this mapping continuous? Is it even homomorphism? And I think I saw that in the notes, so I think at some point here we'll answer that. All right.
Thank you for my talk. I think there's plenty of candy left, so if you have questions, feel free to ask them.
Please go ahead.
So in the end, you mentioned that this von Neumann algebra construction is functorial. Is it even left adjoint functor? So in the case for group algebras, the group algebra functor is left adjoint to the unit functor.
Can you say explicitly what that would mean? Right, so left adjoint to what functor?
So in the group algebra case, when you have a C algebra, you can consider the group of its inverse. And this is the functor from C algebras to groups. And then the element says that you want to write on C algebra morphism from a group to an algebra. This is the same as a group homomorphism from this group to the group of units of algebra. So there's something similar.
I don't know. From my past experience, these nice categorical things usually don't work super well in context of differences, but this might, I don't know. Oh.
John, any question?
Yeah, I'm just, it's not so clear to me why I should take this as a limit for a limit sup.
Yeah, that's a great question. I mean, so somehow what we remarked is that this topology is stronger than this one, right? So this should be a smaller space than this one.
Yeah, okay.
But that's all,
Yeah.
that's, I don't know.
Good answer.
There is a question chat, is do O1U and O2K generate two different topologies, or are they generators for the Jagati topology?
Oh, yeah, that's a great question. I think they both together generate the topology. So you need both kinds of open sets.
Will we learn some stuff about what kind of topology it is? Like, is it Polish or anything?
Yeah, that's Polish.
It is Polish. Cool, thank you.
Okay, if there are no more questions, let's thank the speaker again.